Okay, this is lecture number 6 for Geology 2017. In the previous lecture, we've been working on a general set of concepts that we're dealing with viscosity mostly, so understanding the role of viscosity in a number of processes that include mainly volcanism and the production of a variety of volcanic ejecta or tephra in general was really at the core of the previous lecture. If you remember, we distinguished two main types of volcanoes. So on the top there you have the Strato Volcano. We mentioned the Strato Volcano in the second part of the lecture. We were sort of comparing them against the shield volcanoes, which are much more extensive. Yes, the first really difference was this idea of the changing steep, which is above the 10 degrees for the stratovolcanoes, and that is strictly related to the viscosity of the magmas. So there are a number of differences that we can recognize to sort of review this distinction between different types of volcanism. And when you have less viscous magmas, such as basaltic lavas, you tend to have, especially in a hotspot setting, very broad accumulations of basaltic plateaus, and also you form these shield-like accumulations, which are so extensive that sometimes they even influence the oceanic crust. And these are major sort of supply zones for magma, and they are quite dynamic, as we saw. So it's important to make examples such as Mauna Loa, and you can see really the distinction. It's a shield volcano is roughly 10 times in terms of size and volume if compared to let's say the Mount Rainier example here, which is only 18 kilometers wide. The edifice, the structure of these volcanoes is also very much different, with here more homogeneous products. So essentially it's a sequence of lavas. So we saw the distinction between lavas and pyroclastic deposits, and we saw also that there are different types of pyroclastic deposits, so the surges as well as the fallout deposits. So in this context, the type of activity, the style of and size of magmatism are well distinct, but a question that we could ask ourselves is, are these volcanoes occurring in specific tectonic settings, and what is the budget in terms of amount of magma flow that they are contributing to. And so it's important to realize that these are not single volcanoes. They will represent commonly a system of multiple volcanoes with this style. So if we have to look at their budget in terms of magma production and how much essentially they contribute to the crust, it is important to get a perspective that is a broader perspective and give us the feeling really of the volumes of magma erupted in the different tectonic settings. So we have discussed extensively tectonic settings in I believe the second lecture, and so here we're going to review some of these environments and try to link them to the origin of volcanoes. I think it's important to realize that the majority of the volcanoes, so approximately 95% of the volcanoes, are found on continental or oceanic margins, so at the margins of the plates, basically, which is expected from previous discussions we had. We know that, for example, in a subduction zone, like this example here, which is related to an island arc, so oceanic plate is subducting other oceanic plate in this example. It is quite often the case in which you have dehydration of the subducting plate, and this, we said, facilitate the development of magmatic chambers. All right, the same we said for mid-oceanic ridges. These are discontinuities in the crust that tends to lead to major production and continental growth. And in fact, up here you have a couple of cubes that gives you essentially the relationship between extrusive magmas and intrusive magmas. And these are volumes expressed in cubic kilometers. Okay. So, of course, since this is the area of production of crust, the majority of the volume of magma is produced in these very extensive domains. You have also to think about the size of a mid-oceanic ridge. It is indeed much bigger than a system that would be representative of, for example, a seamount chain. So if you are either under continental or oceanic crust and you have hot spots forming, those usually will lead to volumes that are much lower. So in this particular case of the seamount chain, we have essentially a production that is of roughly 2 cubic kilometers per year in terms of intrusive rocks and 0.4 cubic kilometers for the extrusives. So you can see roughly, on the order of probably one-tenth of the production of intrusive rocks if we make a comparison with the mid-ocean ridge. So why is that? In essence, we have seen that the cases like the Hawaiian Islands are more restricted, okay? So they don't extend their extent is not really as much as a mid-oceanic ridge, which extends really for the entire globe, basically. So from pole to pole. So because of that, you have, of course, a much larger supply zone, and this is why you have such large budget for the supply of intrusive and extrusive rocks in mid-oceanic ridges. The other aspect is that is very similar in terms of volumes. We can see that, and we could argue that we have similar processes. Plume-related magmatism is often invoked, so deeper magmatism is invoked for seamount chains, so hotspots, and also for volcanism that occurs intraplate in a relatively stable platform on a continent. So these are budgets then that are comparable because of the amount of magma production and the fact that it's more localized. So that gives you sort of the feeling of the relationship between the amount of magma production and where you locate volcanoes in different continental settings. So remember these four environments, so consuming plate boundaries, which could be either oceanic or continental, divergent plate boundaries, so the oceanic ridges, intraoceanic plates and intracontinental plates, so these are more hotspot-like events. So in this context, what is critical now is to think about the different types of volcanoes, and already we are able to realize that stratovolcano, because of the extensive silicic magma supply, will be likely related to situation in which you have thicker crust. So the optimal would be this situation in which you have oceanic crust producing the volatiles, and you have magma that develops within the mantle wedge, and then you have this thick continental crust that is highly silicic, where you have a lot of partial melting taking place. And so you tend to form stratovolcanoes in these conditions because of the fact that you have a lot of continental crust that is involved in the ascending magma process and magma production. In light of that, these other environments, so the mid-oceanic ridges, will be rather, promoting the development of seamounts and so volcanoes that are more shield-like volcanoes, because they are more basaltic in composition, or dike complexes of plateaus will be forming in mid-oceanic ridges, as well as in oceanic related seamount chains, which are the hotspots again. So in those scenarios, you will find those shield volcanoes. So we are able to see really these different trends and understand where we can place different types of volcanoes. But those are not the only it's not the only way in which we classify volcanoes. There are also other ways in which we classify volcanoes, and those are dominantly based on the type of eruptions. Okay, so if we think in terms of shield volcanoes, we will have dominantly Hawaiian eruptions, but we also have situation in subduction related environments that involve oceanic crust that are relatively non-explosive. So in this case, this classification based on eruption times, eruption types is really linked to this concept of the volcanic explosivity index. So what we are doing is to look at sort of different types of volcanoes and try to distinguish them based on their explosivity, really. So this Strombolian type is very similar to Hawaiian eruptions because it does have, for example, shower of lava fragments that are quite often. It's a type of sort of eruptions that are fairly continuous, and they have lots of liberation of gases because the lavas are relatively non-viscous, so they're mostly basaltic. So in response to that, you have even in a subduction-related tectonic environment, you can still form relatively quiet volcanoes, so that they have no major explosive activity taking place. And this could be, the cinder cones we were mentioning. So often you have this cinder activity and production of scoria that is quite typical of these Strombolian volcanoes, with the type locality in southern Italy. So Stromboli, it's giving the name to this type of activity, which is one of the islands in the Tyrrhenian Sea on the southern coast of Italy. We will see some examples of that later. Volcanic eruptions are in the same type location. So there is an island called Vulcano that is characterized by this eruption, which are more a compromise between very explosive eruptions and the very quiet, like the Hawaiian, with a lot of lava production. So this is more a mixed type with more discontinuous eruptions, and usually you have ash columns that start to develop, but quite often when we try to evaluate the explosivity, we look at the eruption column height, and in this particular case for the Vulcanian eruption it's on this front here, so it's on the order of less than 20 kilometers, and also you have production of something that is sizable in this. So in this lecture we will see that we have different types of ejecta that are emitted during volcanic explosions, and these can be classified by size. So some of the largest fragments are called blocks or bombs, and they are part of the activity of these volcanic eruptions, and they are another way in which we can establish the strength of the explosion. Sometimes you rather refer most commonly to the volume of ejecta, so combinations of tephra. If they, for example, exceed 1,000 cubic kilometers, we get essentially the most powerful eruptions on Earth, which quite commonly have a volcanic explosivity index of 8, which is really the top. So these are likely eruptions that you will never experience in your lifetime, because they occur every 10,000 years. So the frequency of it is interesting to realize that the frequency of eruptions is essentially inversely proportional to the volume of emissions. So the larger and the stronger is the eruption, the less likely it will be developing very frequently. This is somewhat because you need to charge in a way the system, so increase progressively the amount of pressure, and it is in exceptional circumstances in which you basically create a rupture and you have this release of energy that causes the explosion, really. So usually there is a big paucity between events when you have very explosive magmas. So these are more frequent, and so very low waves, so Hawaiian eruptions, for example, are quite frequent. You can have even eruptions on a yearly basis that takes place. So they're much easier to see, and in fact a lot of tourism that we have on the Hawaiian Islands looks really at exploring the fascinating aspects of the shield volcanoes, and many times people get interested in seeing the lavas, for example, when it reaches seawater. So that's because you get some fantastic sort of steam eruptions, and it's quite exciting to see that because it always results in lava fountains, for example, and some degassing and explosive activity. Before I forget, we have also the subplinian and plinian eruptions. These are the most explosive eruptions, and they have usually ejecta that exceed the 20 kilometers in elevation. Quite often the plinian are between 20 and 35, and yes, they are really distinguished by the fact that they develop the pyroclastic flows. So you will have higher magma discharge, and this is sort of the result for both the plinian and ultraplinian of the intense devolatilization that takes place. So you tend to have quite a bit of scenerites, and this can lead to characteristic eruptions. For example, the production of lahars, which are massive flows of mud, and also the accumulation of large amount of scenerites, even distally from the site. For example, when if we think of the very large events approximately 30,000 years ago in the topo volcanic zone in the Northern Island in New Zealand, we recorded a very large eruption, and this had actually scenerites being deposited approximately 1,000 kilometers away from the center of the caldera that led to a massive explosion. So these activities that are basically very rare can lead to massive accumulations of scenerites. Some of the exposed scenerites in New Zealand exceed the 200 meters, which is really exceptional, and it's a good indication of how much a volcanic eruption can influence the surrounding geomorphology. So even with the example of the Mount St. Helena in the States, this has seen massive changes to the cone of the volcano. So most of the top part of the volcano got destroyed, and this is has been attributed to a wave of 4. So it didn't really had in reality any comparable means with respect to this super large eruption that occurred in New Zealand, but still it was an incredibly powerful eruption. So yes, it's important for volcanologists to understand the explosivity of volcanoes, because of course you can base historical records and you can reconstruct basically the history of volcanism in specific areas, and you will be able then to evaluate the risk associated with the style of volcanism and the relative explosivity for future events, so that you can prevent loss of life as well as mitigate the impact on the environment if you can. So we see now some examples of the key types of volcanism that we just described, so that we learn a little bit about volcanoes in Europe as well as in other parts of the Earth, such as the Aleutian Islands, for example, or the Caribbeans. Essentially, all the plate margins are critical, and also it's important to learn the fact that the majority of the volcanoes are not as easy to reach because they are many times submarine volcanoes. So they concentrate, for example, on clusters along the oceanic ridges, and so you will not see them unless they become essentially they emerge from seawater because of the large accumulations, which is what happened, for example, to the Hawaiian volcanoes. In the beginning, they were submarine volcanoes, but then by accumulation of subsequent events, we get thick accumulations of lava that then render the volcano subaerial. We'll see some examples of that evolution as well, which is quite interesting because it does change dramatically the style of volcanism. One of the most renowned localities for volcanism is a region in Europe which is part of southern Italy. It's essentially distinguished by a variety of styles of volcanism, and these are subdivided into key localities. This area here, the Campi Flegrei and Vesuvius, are termed as Roman volcanism. Instead, down here you have a large archipelago, so the archipelago of the Aeolian Islands, and these are the main centers of volcanism in this part of Italy, that are essentially the result of subduction related magmatism, or are actually attributed to subduction, although here the tectonism is quite complex. We have essentially a collision between the African plates and the European plates here in the northern part, and you can see here a trace of the subduction that illustrate the complexity of the plate interactions. I think it's critical to illustrate the arc-like geometry of this part, so the Aeolian Islands. I will spend some time understanding the different style of volcanism. In this map you have different accumulation of volcanic products in the main islands. So we will review the Stromboli Island and Volcano, because these are the two islands that are related to the classification that I was mentioning earlier. And also we will discuss about the Etna Volcano, which is also distinct from these two main volcanic fields, because it's a stratovolcano that has a much longer history. These two centers of volcanism are more coeval, and they are relatively young, so from present day activity to, I think, the oldest eruptions in this Aeolian arc are more on the order of 1.3 million years, or even less than that. So the majority of the volcanoes have ages that are on the order of 500,000 years, so 0.5 million years basically. So if we look at this cross section, you see here a cross section through Sicily. We can see the equivalent in this image. So this is roughly 200 kilometers depth, and we have essentially the Aeolian Islands with Stromboli emphasized in this section on this part of the crust, and the Calabria, which is this region of Italy that is on this more eastern side of the promontory of Italy. It's well evident the fact that you have essentially north to northeast trending, no, actually north to northwest trending subduction, which is corresponding to the Ionian slab. And one of the characteristics is that at relatively high pressures, here we have the liberation of fluids from the top part of the Ionian slab. There are two stages, the supracritical liquids and aqueous liquids. These are sort of higher pressure domains, which leads to an emulsion basically of fluids and gases, and hence the terminology, so supercritical, stands for essentially a mixture of a single phase, more correctly, of gas and water together. and after you decrease the pressure of a few gigapascals, you enter this field that is more represented by aqueous fluids. So these will have different roles in terms of interacting with a mantle wedge, which will lead to different styles of magmatism, including some of the magmatism we observed in Stromboli. And in fact, Stromboli is, characterized by a variety of magmatic rocks, from the calcaline to the potassic, so strongly potassic assemblages, and also shoshonetic magmas. This is a little bit too sort of detailed, but keep in mind, based on what we discussed so far, that you can have partial melting occurring at different depths, and this will lead to different levels of enrichment with the crustal components, which leads to different fractionation trends, and so you have dominantly calcaline series here, which will be essentially an indication that there is a crustal component, as well as more magnesium-rich magmas that are, as I stated earlier, those, for example, basanites or picritic basalts that are more an indication of sort of deeper melting and less crustal influence. So these two end members are present, and we are going therefore to review this archipelago because it does offer a variety of examples of volcanism. We will then move to look at these domains with the Vesuvius for the strongest style of eruption, so the Plinian eruptions. Okay, the first volcano that we review is Stromboli. It's a small island in the Tyrrhenian Sea off the north coast of Sicily, containing one of the three active volcanoes in Italy. So only three of the volcanoes are active at present. And yes, it's part of the Aeolian Islands, which is again a volcanic arc that is found in northern Sicily. This name Stromboli is derived from the ancient Greek name Strungul, which was given to it because of its round swelling form. The island's population at present is on the order of 500 people, so not many inhabitants, and the volcano has erupted many times and is constantly active with minor eruptions. You can see here some examples of these minor eruptions, represented dominantly by lava fountains in which we have cinerites that are produced, as well as some minor lava flows. And you see here this flank that has been recently characterized by volcanic activity, with examples here from 2003 lava flows that essentially are emanating from the central crater, and they interest the northwestern part of the island. So Stromboli's most recent major eruption was likely in 2009, and the volcanic island stands at 926 meters of elevation, so roughly 3,000 feet above the sea level. And yes, significant geological features of this volcano is called Sciara del Fuoco, which means streams of fire, which is essentially a big horseshoe-shaped depression generated in the last 13,000 years by several collapses, mostly on the northwestern side of the cone. So those that was illustrated in here. So it takes the shape of an horseshoe, and also this characteristic fountain has sort of gained the nickname to Stromboli of the lighthouse of the Mediterranean, which is because of the fact that from the vessels that pass along the coast, you can clearly see this volcanic activity, especially at night. Okay, we can consider the next example, which is this example of the Bandera Volcano in New Mexico. So the Bandera Volcano is part of the Zuni Bandera volcanic field, which is more correctly in northwest New Mexico. We are considering this because, like Stromboli, it does have a history of basaltic magmatism, which had quite a bit of cinders forming, and so cinderites, so those pasty lavas, which are very similar to the activity that you find on shield volcanoes as well. So many episodes of basaltic eruptions which happened over the last million years, and yes, it's a large volcanic field. It extends for 90 kilometers and essentially has produced many basaltic lava flows, which have both the AA type and Pahoehoe type flows, with lava tubes as well, and also, most importantly, the cinder cones. And in this figure you see an image of a very thick pile of cinders that represent the extensive accumulations of these basaltic products. So the Zuni Bandera is essentially an excellent site because of this for studying volcanology, and I would say it's quite unique to have this opportunity to see a Hawaiian style volcanism in the States. So in this context, it's important to remember this example of cinder-like features. So many times the ejection of lava that is very hot and siliceous can lead to interaction with the air that will form this fibrous lava, very sort of rough and in texture, and this is commonly called the Pele's hair because of that. Pele is a famous goddess of the Hawaiian Highlands, so that it's part of the myths of the Hawaii, and she's the goddess of the volcanoes, basically. Other features are these characteristic tears. So they are elongated with a large base, and that's looking like a tear, basically, that has solidified and is dominantly made up of glass. So this is obsidian, basically, or volcanic glass. So you can produce volcanic glass also in basaltic eruptions when you have a lot of ejecta forming during cinder cone development. So this Bandera Volcano is very similar. It does have lapilli-size scoria fragments, so cindery appearance, and essentially the deposits is very near the scoria cone, basically. So these accumulations are very, very close, only a few hundred meters above the venting site. So it's a good example that is worth visiting also for the lava tubes that are quite famous because they are often filled with ice, which is quite interesting, and they have been mapped extensively for several kilometers. This example shows sort of reiterates the concept of cinder cones, and we have a couple of shots from the Lassen National Park in Northern California, which shows this characteristic cone that is very typical of these cinder cones, as we discussed already for some of the Italian examples, and also down here you have the Puo. Essentially it's another cinder that is quite active. It's been active since the 80s, and so it's one of the most recent really continuous eruption on a shield volcano. I think this Puo is a small vent that essentially formed this cinder cone as part of the Kilauea volcano, which is a very large sort of shield volcano, which is part of the history of one of the southern islands, so the big island basically in Hawaii. So these are good examples here because of the inclination. So the slope, it's quite steep, which is a good indication. Single type of products. This is actually a famous locality for hiking. If you look carefully at the image, you can see the trail, and so you can walk up the trail, and it's quite scenic to sort of have a look out because of the extensive magma flows that are visible from the top of the volcano. And this area is very nice because of these spatters of lava, which are really dangerous. So certainly you don't visit when you have this type of activity going on, but from distance at night it will be certainly a fascinating sight. Let's move to the next example, which is Volcano in Italy. So we are kicking up the explosivity. Volcano is more complex than Stromboli. It does have a long history of magmatism that has seen the migration of the volcanic activity with the significant paucity among the different eruptive stages. So Volcano is located roughly 25 kilometers north of the big island in Italy, so Sicily, and yes, it's located at the southernmost end of the 8 Aeolian Islands. So the island is roughly 21 square kilometers in area, and it does have a slightly lower elevation if compared to Stromboli. So it's on the order of 500 meters, so 1600 feet roughly above sea level. It contains several volcanic calderas, including one of the 4 active volcanoes in Italy that are not submarine. So this is a subaerial caldera, and the word volcano and its equivalent in several European languages derives from the name of this island, which in turn derives from Vulcan, the Roman god of fire. In the last 6,000 years, the Volcano Island has recorded on the order of 9 major eruptions, so it's far less if compared to the continuous activity that we find on the Stromboli. At the north of the island is Vulcanello, 123 meters high, and you can see also a view of the different volcanoes here, looking north and also looking south. And so if we look south, we see basically the big Il Piano caldera in this case. Okay, from a geological standpoint, the volcanic activity in the region is largely the result of the subducting plate we showed previously, so the Ionian plate, that is essentially the African plate that is going under Eurasian plate. And Volcano has been quiet since the eruption of the fossa cone on the 1880 or 1890 roughly, with this eruption depositing on the order of 5 meters of pyroclastic material on the summit of the volcano. The style of eruption that interested the fossa cone is commonly called a Vulcanian eruption, which is what we mentioned when we were discussing the different styles of volcanism. And this is because it's explosive and produces pyroclastic fragments of viscous magma. So the high viscosity is essentially controlling the explosivity, although if you remember, the column of ejecta is less than 20 kilometers in elevation, so it has an intermediate explosivity index, so the V is quite low. And so here you have still a volcano with some classic fumaroles, so you can see the vapor emissions and some sulfur that is deposited where these cavities or vents are actually located. So a fumarole is a hot gaseous volcanic vent, and yes, Volcano was constructed during 6 volcanic stages, and it took roughly 136,000 years to develop the different calderas we discussed, so the Del Piano and della Fossa, and also Vulcanello. Here is another picture that shows a better image of the classical crystallization of Safa, which often has a resinous luster, and it's rhombic if found in eohedral form, and however, often in the fumaroles, especially if they are submerged, you will have characteristic acicular development of sulfur or dendritic examples. So this is all native sulfur in different essentially morphologies and habits. We can talk about now the Mount Etna, which is the tallest active volcano in Europe. This is a beautiful figure that shows Sicily, and we find essentially the Etna volcano with this very extremely large footprint, essentially extending on the eastern coast of Sicily, where the town of Catania is found in its southern part. The Etna volcano has a basal circumference of roughly 140 kilometers, which gives you an indication of really its history, I would say. So originally it was a shield volcano that then turned into a stratovolcano. Because if you look at the footprint of the stratovolcanoes, as we were discussing at the beginning of the lecture, it's usually 1/10 of that. So we were talking about Mount Rainier, and we saw it has 18 kilometers roughly. So this volcano is very large. It's kind of an unusual stratovolcano because of that. And also it's extremely tall. So as I said, it's tallest in Europe, and so with this approximately 3,329 meters, it's on the order of essentially 2.5 times of the Mount Vesuvius, which is also quite remarkable volcano in Italy, as we will see. Etna is famous since the Greek times. In Greek mythology, it was sort of thought as a volcano where the deadly monster Typhon was trapped under essentially under his summit. So this is to suggest that Mount Etna is really one of the worst, most active volcanoes, and since those times it's been extremely active. So an example of its activity is really seen in this figure, because you can see a smoking chimney with the smoke transported by the winds towards the eastern coast of Sicily, and then sort of encountering the southern part of Calabria. So this is a good indication of activity that is continuous over time. If we look at the history of eruptions, we have really a number of events that is quite vast, because this volcano is very old. Initial evidence of activity starts around 500,000 years ago, so 500,000 years, and roughly between 300,000 and 170,000, Etna will become a stratovolcano. So it renders this volcano quite unique in a way, because we have sort of a mixed set of cyclic activities that are alternating between explosive and effusive eruptions. This will be again a function of the liberation of gases. If you start to have situations in which you increase pressure and reduce the amount of emission of gaseous emissions, it's more probable to develop explosive activity. So Etna experienced some very explosive eruptions, not only basaltic eruptions, and in these explosions it did generate large pyroclastic flows. If we look at the complex set of volcanism that develop in terms of morphology, we see that we have a main crater at the center, but also small craters and cinders have developed all around the main cone of the volcano. Another feature that is manifested on the eastern side of the volcano is the Valle del Bove, which is a major caldera that developed in a fashion very similar to what happened at Mount Sainte Hélène. So in essence, you have the collapse of the dome and subsequent landslides that develop, and also pyroclastic flows are quite common in this type of volcanism. In terms of the most recent events, we could start with the 122 BC event that interested the city of Catania. Again, it's slightly south of of the Etna, and this was a tephra eruption, so a lot of ejecta, and it was very explosive and caused quite significant damage to the city, so that the Roman government exempt the population from paying taxes for 10 years. Another major eruption that is worth mentioning is the one that occurred in the 1030 AD near Monte Ilice on the lower southeast flank, which produced lava flows that travel about 10 kilometers and ultimately reached the sea north of Acireale, another village in the area. Probably the most famous is the 1669 event. This event produced extensive lava flows that destroyed at least 10 villages in the area, and it was mostly concentrated on the southern flank, and ultimately it reached the city walls of Catania, and it took roughly 5 weeks to do that. The lava was luckily diverted for the most part by the city walls, and the lava ended up south of the city, filling the harbor of Catania. Unfortunately, there was a fragile section on the city walls, and because of that, the lava was actually able to destroy some of the buildings until it stopped on a famous Benedictine monastery without touching it. Few deaths were reported, but these are also debated in literature. Then we have the Mascali Eruption, which is kind of a minor, one of the most recent events and one minor sort of eruptions, and I think the event was used by Mussolini as purpose for propaganda, as part of the evacuation program and aid and rebuilding operation that were particularly successful during fascist times. Other eruptions are known for reaching distances that are quite exceptional. For example, the 2003 eruption that reached Libya with the degassing processes. And then we have the 2007 Catania Fontana Rossa event, which is even more important and recent. So I think we can move to Plinian eruption and discuss Mount Vesuvius. We will have sort of a discussion of the different phases of a Plinian eruption as an introduction to the AD 79 eruption that occurred on Mount Vesuvius, which is near Naples. This is a quite important eruption because of the number of lives that were lost and the fact that two major towns in Campania were completely destroyed. And so these are the famous Ercolano and Pompeii. So the city of Pompeii was essentially submerged by pyroclastic flows. Okay, as we were discussing, the Mount Vesuvius is roughly 9 kilometers or 5.6 miles east of Naples, which is in central Italy, in the region of Campania, and is in fact a part of the Campanian volcanic arc. So it's one of the various volcanic centers that are also named the Campi Flegrei, that are sort of important in the volcanic history of southern Italy. The most important eruption that occurred on the Mount Vesuvius is the eruption that has been termed Plinian because it's been described by Plinius the Young in the Anno Domini 79. And it's also very famous because it destroyed, as I was mentioning earlier, a number of cities. To be more correct, it destroyed Pompeii, Herculano or Herculanum, and Oplontis, and also Stabiae. So 4 cities as well as other small settlements were destroyed. In terms of number of people that died, it's estimated that more than 1,000 people lost their lives due to the basal surges that are characteristics of these Plinian eruptions. The elevation of the column of Tefra is estimated to have exceeded 33 kilometers. So the volcanic explosivity index of this eruption was either on the order of 6 or more based on these estimates, although they are approximate because of the time of this eruption. This is not the only eruption that the Vesuvio has seen. The volcano has also had numerous other events throughout the centuries, either before in the prehistoric times, but also after. And the last eruption was the one that occurred in 1944. So all these eruptions, however, were never of the same intensity as the one that occurred in Anno Domini 79. So this remains the most historical one, and it is interesting to realize that from 1944 Vesuvius has been in a quiescent state. So it's at present a very sort of risky situation in a way, and is one of the most dangerous volcanoes that occur to be in Europe. The eruptions are very different, so they can vary significantly, but are dominantly characterized by explosive outbursts of the kind found in other Plinian volcanoes. So let's say the example of Mont Pelée, for sake of comparison, is a good fit, or the Krakatoa in Indonesia is also a good example, or relatively recently active volcanoes of similar capacity. In terms of explosivity, you could think of the Anno Domini 79 eruption as it had an intensity that is comparable to 100,000 times the Hiroshima bombing in Japan. So much more than that, and very destructive because of that. In fact, a lot of the top part of the volcano has been completely removed by the explosivity of this eruption. In terms of the processes, you have here a table that summarizes the characteristics of the particles and deposits that form in Plinian eruptions. I'm not going to discuss all these details, but it's instructive to sort of read through and also link this to eruptive and transport processing. For example, the sorting and grain size variations that occur are often related to the fallout of the particles from the eruption column. Other things could be the geometry, again, the distribution of the pyroclastics is usually forming layers, and these are a function of the eruption column as well, because of the energy involved, and so the distance that the different sediments reach will influence the thickness of the layers as well as the sorting. Here are some other images of this massive eruption, and it's quite interesting to see an image here of the old Soma volcanic edifice. So this was termed the Soma Volcano before the 79 AD eruption, although Romans refer to Vesuvius in the mythology, and it was actually venerated and thought as the volcano of Hercules. This is another image that shows the exact Italian terminology would be a nube ardente or nubi ardenti, which are essentially pyroclastic flows, which are extremely deadly because of the velocity. So they exceed 600 kilometers per hour in terms of velocity of movement, and also they usually have elevated temperatures exceeding 600 degrees. So everybody or everything that is on the way of these basal surges will likely get destroyed. Some people were able to hide in certain locations, but they died because of the gases, which are toxic and cannot be really leave you essentially breathless. So often these eruptions are extremely famous because of the state of preservation of life just before the eruption completed, and also after the cinerites were deposited. Because of the rapid sedimentation of the cinerites, you have examples such as this dog that got trapped in the pyroclastic flow and died, and you can see the position in which he was essentially preserved. So that's quite stunning, I think, and worth certainly visiting Pompeii or Herculano to actually see what happened and remember this tragic event. I think there should be more education about this because, for example, on the Vesuvius we have huge cities like Naples that is very close and could be easily struck again by this type of eruptions. So we have roughly 3 million people now around the Vesuvius and area, and yes, you can see here all the inhabitants and their dwellings, so very dangerous. Another example here is the Krakatoa. This is a very close example to Vesuvius because it has an estimated explosivity index of 6. So the eruption was equivalent to roughly 200 megatons, or essentially about 13,000 times the nuclear yield of the bomb that was delivered to Hiroshima. So it's not as comparable to Vesuvius. Vesuvius was even stronger, but this was enough actually to blow completely away an island. So this is the footprint of an island that is located in, I think, in the Kalimantan area, and this eruption occurred in the 1883. So it's roughly 2 centuries ago, and yeah, now the remnants of post eruption is just this little island in the middle, which is this one you see here with a small volcano in the center, which is what's left really of various volcanic centers that were responsible for the dismembering of this island. So the eruption from the Krakatoa in Indonesia forced the evacuation of tens of thousands of residents, and these have been sort of continuing for a relatively long time. In fact, even in 2011, we recorded a similar event. The last example of Plinian eruptions that we are going to review is the one of the Krakatoa volcano. This had several historical eruptions, but the most important that has been recorded in this island is the one of the 24th of August 1883. You can see here an image of the islands that surround Krakatoa, and this is the outline of the island that was comprising three main craters. So the Perbowatan, Danan, and Rakata, and they were essentially the ones that were active at the time of this eruption. You can see here what's left. So in orange we have the new island, which is a small island represented here with a remaining crater, and this one is the new Anak Krakatoa, and basically all this part of the island, which includes these two main craters, the Danan and Perbowatan, is no longer in existence. It's been essentially destroyed by this eruption of the 1883. So this eruption is particularly important for this region, which is essentially in the Sunda Strait, which separates the Java island from the island of Sumatra. It's important because of the explosivity index, which is on the order of 6, and in fact this explosivity was so high that it's again being compared as the Vesuvius to the nuclear yield of Little Boy in Hiroshima. So very strong eruption that is more than 10,000 times stronger than a nuclear detonation, and because of that it was heard even at more than 3,500 kilometers, or actually more than 5,000 kilometers, because yes, reports of the noise were were actually mentioned both in Australia, so in Perth and Alice Springs, as well as in the Mauritius Islands. So these were roughly 5,000 kilometers away from the center of eruption. Other evidence, of course, is the extensive volume of material that has been compromised by the eruptions, as well as the style of eruption. So we have a big column of tephra that forms, and in fact it's been postulated that it reached 80 kilometers of elevation, so even higher than the Vesuvius, which, if you remember, was on the order of 33 kilometers. So very strong and powerful, and some reports argue that if you were standing 16 kilometers away from the island, you would have gone completely deaf because of the sound. And yeah, this is part of the explosivity of these eruptions. In terms of recent eruptions, this andesitic volcano had an eruption in 2011 on the new volcano, so the again the Anak Krakatoa, and this led to the evacuation of tens of thousands of people, and this affected roughly 7 districts. This style of activity was again ash emissions reaching heights of roughly 600 meters, which drifted in an easterly direction. So you can see here some evidence of previous eruptions on the island, and some of the lavas that are actually lobated and reach the seashore of this island. So quite good example of a Plinian volcano, actually a almost super Plinian volcano. We have concluded now the review of some of the key volcanoes, just to give you sort of a flavor of this lecture in terms of reviewing the history of the most famous volcanoes on our planet. This is particularly famous because it's one of the strongest eruptions that occurred in the last few centuries, really. But now we are going to look at the summary of the different types of products and some of the characteristics of key volcanic products that are resulting from these eruptions. So we start by looking at pyroclastic rocks. So of course a pyroclastic rock is a rock that is part of a Plinian eruption, and this diagram is useful because it gives you sort of a summary of the different processes that occur in the beginning. So processes of pyroclastic flow initiation are listed, as well as the characteristic pyroclastic flows and also the resulting deposits. So there are essentially 3 phases in this process. So when we start, so initiate an eruption, usually you have phenomena such as subsidence of the eruption column that accelerates the velocity of the flow, boil-over effects in which you have a sudden liberation of gases, and then you have cases in which you have inclined eruptions or dome collapses that are related to those spine volcanoes that we mentioned earlier, as well as the example of Mont Saint-Hélène with this central dome is quite instructive So in essence, you need to release pressure, and that will start to trigger liberation of gases. Explosive activity comes with that, and a lot of rock gets fragmented because of the release of energy. This fragmentation will lead to the formation of ash flows, ash clouds, pyroclastic surges, and the news ardents, which is the nubi ardenti I was mentioning for the Vesuvius. We saw that interesting image of the city of Pompeii under fire with these massive pyroclastic flows. What are the type of products? The type of products can be depending on a number of factors, but for example, the mixing with water. So if you have lakes involved, like Mont Saint Helene, you can form lahars, which are mud flows, and then if the water is not really involved, you get ash flow, which usually forms these tuffs and breccia. So a lot of glassy material accumulate pretty much like a sedimentary rock, and then you have ash clouds or pyroclastic surge deposits, which are more chaotic because of the energy involved with the transport of very rapid transport of material, which is usually a mixture of gases, tephra, and also lapilli are quite commonly present, as well as other things that we will see in the next slides. If we look at the subaerial processes, quite often you have an eruption column that forms, and this will lead to cloud turbulence, and this usually supports relatively small size fragments. This can be sort of transported with the wind for significant distances, and then they will precipitate and contribute to the pyroclastic flow deposits as well. So you form cinerites quite often, especially distally. So how do this thing look like? You have an example here of a Plinian ashfall. So when you have cinerites depositing, they usually form diverse strata, and this is an example of a concordant stratigraphy of tuff layers. So if you remember a tuff, we mentioned pumices, tuffs. These are all rocks that are dominated by volcanic sediment that is essentially represented by fine particles that have been ejected by the volcano, and these are commonly cinerites. So they are very glassy, and they can have a variable grain size depending on the energy of the eruption stage. So in this case, you can see different phases of tuffs in gray, which is more fine-grained, and then you have sections in which you have more tuffs that are more coarser in size, and you can even recognize some grading, especially in this layer here, with fragments of considerable dimension, so exceeding the centimeter scale, and then you have smaller and smaller fragments, and this is again linked to the energy of the eruptive stage. Usually you start with a big burst of energy, and then the process wanes off, and this is really translated in the capacity of the volcano of redistributing coarse material in its early phase, and then subsequently leads to the deposition of finer fractions of sinerite. Some other examples here illustrates the effect of tectonics. So many times you can have multiple eruptions over really decades or centuries, and of course in the middle you will have stages of tectonism that can deform the crust, and this can be recorded by recognizing the unconformities, which are essentially surfaces that represent discordant events. So in this case we have a first phase of eruption and we form some tuffs, and then some tectonism will tilt the topography, and so you have a situation in which this surface becomes the top surface and it's an erosional surface, so you truncate the existing volcano sedimentary stratigraphy and deposit another layer or another set of layers, more correctly, of tuffs on top, causing a situation that sort of highlights this condition, which is termed unconformity. We have different types of unconformities, but yeah, let's assume that this one is an erosional unconformity because of this major truncation. This is another example of grading that I was mentioning before. You can see here accumulation of volcanic tuffs with again coarser size, fraction, and finer, intermediate here, and then finer in this more whitish tuffs, so very silicic tuffs. Other examples of important accumulations of tuffs are the ones that are found in Greece, especially on the Santorini Islands, which is located in the Aegean Sea in Europe. So there are really hundreds of islands in the Greek archipelago, but yeah, this one is particularly famous for the Red Beach, which is a site in which you can observe a very thick sequence of volcanic sediments. So this is also famous because the explosion of Santorini, which blow off the island, this island is very attractive because you can actually still see an active volcano in the middle, but it's like an half moon, because similarly to Krakatoa, essentially the central part of the island blew off during this major eruption. So the Terra eruption that is dated 3,500 years ago roughly, and so this triggered apparently from mythology a major tsunami that reached actually the another island that was completely destroyed apparently, and was essentially causing the end of the Minoan civilization. So Europe is also important from the volcanic perspective because of these earlier eruptions in really ancient history, and this one have these beautiful accumulations of iron-rich tephra, which can be seen also in here with all the oxidation and erosion that is taking place now in relationship to the easiness that you have in destabilizing some of the mineralogy of these volcanic rocks. Here you have some examples of the different sizes. It's really important to realize that depending on the explosivity, you can eject things that are called lapilli, and these are relatively small, usually less than 64 millimeters in diameter. Then you have accretionary things that commonly can form and they will be usually forming in the chimney, so on the phase of ejection, in which you have a big column of tephra that develops. So you can have even finer things. So we talked about these cinerites. These will be less than 2 millimeters usually, and then you have all a range of bombs that have a variety of sizes and shapes. The shape usually is a function of the trajectory and travel velocity of the bombs. Quite often bombs that travel fast, they'll get essentially shaped by the action of the air that is cooling also the hot, relatively hot magma that has been ejected. They also form crusts that are usually compared to bread crust. In fact, this is a bread crust bomb example, and sometimes they can be extremely large, like the Papua New Guinea examples, in which bombs have been recorded of the size of a building, of a house, or like this guy here. This one is quite big, as well as this one here, which must be relatively light considering that is lifting it. Anyways, remember that bombs tend to cool off rapidly, and often you have degassing also that is visible on the crust, and so those are good indications that can help you identifying a volcanic bomb while you are mapping for these features. Here is a classification that is quite often used by geologists, which essentially summarizes the differences between lapilli stones, tuffs, and pyroclastic breccias. So we have essentially that the lapilli will be between 64 and 2 millimeters. Usually you mention a tuff when you have less than 2 millimeters, so a cinerite. And then here you have blocks and bombs at higher diameter, usually more than 64 millimeters. Of course, in the middle, since this is a ternary diagram with so many of those for the classification of rocks, you have also good examples of a nomenclature that can describe a mixture of these three end members. Pyroclastic terminology is commonly used by volcanologists, so it's worth having a read at this table and remembering some of these terms. Quite often we have to make a distinction between loose sediments and loose ejecta versus consolidated material that forms rocks. So for example, if we have lapilli here, these are unconsolidated, but the equivalent in a rock form. So if I accumulate a significant amount of lapilli tephra and I form a pyroclastic deposit of this type, usually after lithification, I will call it a lapilli stone. And here you have other similar examples. So ash or cinerites will become tuff, and other things like a block or a bomb commonly becomes a breccia or an agglomerate. Here are some other examples of volcanic bombs, how they essentially appear in the field once they fall, and you can see they form these characteristic crusts, and these are of basaltic compositions because they come from a cinder cone. Another big example here, big bomb with the classical crust that has been termed bread crust. This is another picture that shows another type of volcanic bomb, which is more lithic and carbonatic in composition, so this is why it's so white. Often a carbonate can play a role in controlling the appearance of this tephra. Another classification that is commonly used is for hydroclastic rocks. So when we have the interaction of the tephra with seawater, so you have the same type of processes really that are taking place. So we will have an initiation of hydroclastic flow. So I said seawater, but it could be also fresh water as well, like the case of the Mont Saint-Hélène. So you can mix essentially any kind of tephra with water, and the result will be either a base surge or a base surge deposit, or essentially a lahar that starts to form and generates an hydroclastic flow until it finds a location where it deposits a massive amount of mud. Here the story is the same. I mean, we have that eruption clouds form, so you can have a range of fallout deposits that can be transported significantly by the wind. So the difference is really the type of deposits, which are more hydroclastic flow deposits that form together with pyroclastic flows as well. Here is some examples of these pyroclastic flows that involve ice or water. So I think this example is from Iceland, and it's just showing the triggering of landslides that subsequently become sort of mud flows that will inevitably essentially redistribute volcanic products at a longer distance. And so often we talk about volcaniclastic sediments as they are essentially formed by a mud flow that involves both sedimentary products as well as volcanic products. And in this particular case, you can see a bomb entrained in this mud flow deposit. So in summary, you can essentially redistribute volcanic products if you have subsequent processes that leads to an hydroclastic flow, for example. Other characteristic products of an eruption are the accretionary lapilli. These are lapilli that are commonly spherical, and this is glassy, and this is because they form initially as droplets in the column of tephra. What happens is that the water droplets tend to attract scenerites, so these will stick to the droplets and it will form a center of nucleation that start to roll with the energy, and so this will be supported by the energy of the eruption for some time in the tephra column until this lapilli gets so big that they become heavier and heavier, and they will start to fall. So an accretion lapilli will form by accretion of wet ashes into circular shells, and so raindrops falling through an ash cloud may collect concentric layers of fine ash. So this is exactly what I was mentioning. You have a cross section, or more correctly a thin section of these accretionary lapilli, in which you can can recognize this concentric accumulation of fragments of syenerites that become relatively glassy and form these spherical, larger size lapilli. Pyroclastic surge deposits are instead more complex. They commonly involve a stratification. Okay, it makes sense if you think about the energy and the dynamic of a pyroclastic flow. So the first layer will be represented by a deposit of primary block and ash flow deposits, which will be thicker and usually coarser in size. And then you have the syenerites that come after. So the deposit of the ash cloud, which is much finer grain, represent a good example of the fallout process. The ash cloud will contain accretionary lapilli, which commonly form characteristic layers. In this particular example, we have a layer on the top part of the section. So if you can recognize this type of stratigraphy in the field, you are well positioned to map the distribution of pyroclastic surge deposits. Another example is here with these accretionary lapilli distributed on multiple layers and a more complex stratigraphy. They are here as well, I think. So we got white pumice lapilli overlain by black scoria, and up here we have dune-bedded lapilli and ash deposits with cross-bedding. And so it's important to realize that the complexity of the stratigraphy will have also internal structures that will depend on the condition of deposition and sedimentation of these lapillis. This is another example of how the tephra can be deposited in a subaqueous environment. So I was mentioning seawater previously. So if you have water, so if in a volcano that is sited on an island, you might have a condition in which you have the volcano slope that is essentially very close to the water level, so seawater. So some of the fallout products will end up being floating on the seawater and will form what is called a floating pumice. So we will see that pumice has these characteristics of being very light and having a density that is less than 1. So that's key for the floating. Usually this leads to the production also of glass shards, which are essentially derived from the erosion and contact of floating pumices. Other products include the effect of deposits and lavas that can trigger slump flows. So you have a slump and then flow of sediment of volcanoclastic origin on the bottom of the sea, basically. The eruption can also break the water surface, in the sense that if the cone is a submarine volcano, like the shield volcanoes, for example, in the earlier stages, you tend to form a variety of submarine pyroclastic flows. So again, you can have slumping and form also what are called turbidity currents, which we will discuss when we talk about sedimentary rocks in marine environments. But yeah, pretty much is similar. You can still form pyroclastic flows, and also again the floating pumices are one of the characteristics of this particular type of deposits. When we were talking about glass shards, they are often recognized because of these angular and glassy particles that are usually on the order of less than 2 millimeters in length, so very small. This is 100 microns, so these are micrometers. And yeah, they are formed either by explosive magmatic fragmentation of pumice, because this, if you think of it, this could be just a bubble, so it's just a fragment of a pumice that has fragmented the vesicles, and yeah, they are mostly found when the magma sort of rapidly, like in the Aeolian Islands, you get this magma that eats the seawater at really high temperatures, and so you have a lot of glass that is produced. Quite often these are called or termed hydroclastics, and they have these sort of shards forming, which commonly have these Y cuspated shapes. Tephra can have multiple phases. Here we have tuffs deposited on erosion, so sometimes you can form a gully in a pre-existing layer tuffs, and this can get filled by secondary eruption and additional tephras. An image of the vesicles that are linked to then this formation of glass shards, and is again part of these tufaceous materials. The bubbles often have elongated shapes, if you see, which are a good indicator of the position and orientation of that specific tuff layers. Sometimes they get welded, so you can sort of have a situation in which there is a stratification on the tuff layers that promotes the preservation of relatively high temperature in the tephra that has been just deposited, and so you have a zoning that forms that is termed welding, and it's essentially a location where the silica that is contained in the tuffs tend to form amorphous glass, and these are commonly called flames, and they are found often in rhyolites. So rhyolitic tuffs will have these classic flames of glass, which are an indication of availability of quartz of free glass, basically, and it will get compacted because of the weight of subsequent depositions of tuff, leading to the characteristic aspects of these flames, which gets parallel to the stratification. They are black in color because they are essentially obsidian, and they are a good way to distinguish a tuff. Another example here of the isorientation of clasts which have been subjected to compaction in this ignimbrite, which an ignimbrite is an abundant terminology that is used to describe a rock that is dominantly composed by pyroclastic flow deposits. Some examples of lahar activity: we talked about hydroclastic processes. This is a view of the Caribbean islands of Montserrat. Montserrat had a massive destructive eruption, which led to these accumulations of lavas and mud flows, and the mud flows can travel significantly away from the main crater, and you will find here massive accumulation of muds, as well as here when the slope actually decreases, and very much similar to other sedimentary processes, you tend to form alluvial cones on the sides along the coastline of the Montserrat Island. So Montserrat had really an impressive eruption in the 1997, which is very similar to what we saw for Krakatoa, the Vesuvius. You can see incredible amounts of cinerite deposited in the city of Plymouth, which is the former capital city and major port of Montserrat. Of course, this pyroclastic flow was extremely destructive, and everything gets covered with ash. Some other examples here of this Plymouth Catholic Church entirely buried in lard deposits. So after the cinerites, also mud flows came into place. This is quite interesting, the fact that you can see all these blocks. It's an indication of the force of the lahar. Lahar are really destructive because of their density. In essence, the higher density of the mud flow allows the blocks to float on these mud flows, and as a result of that, the energy involved is incredible, and so you can flatten out any kind of building that encounters these mud flows. So in summary, LR is a volcanic debris flow that behaves like wet concrete and consists of blocks and lapillis suspended in a water-saturated mud. So that's the key strength of these mud flows, their density. Remember that. There are also mixed cases. I was mentioning that before, in which you mix sedimentary rocks. I won't go into much detail with this classification. It's very similar to what we saw for the volcanic rocks, but what will change is this term. So when we deal with epiclastic rocks, we have volcanic but also non-volcanic rocks that are mixed together. So we start to use a terminology that involves that is commonly used for sedimentary rocks. So it involves conglomerate, breccia, sandstone, siltstone. All this terminology, we will learn it when we work in the lab with sedimentary rocks. Here an example of reworked volcaniclastics. This is the Archean Camp Volcanics at Yellowknife Bay, and yeah, it's interesting to see how these fragments have been rounded and elongated through a variety of processes, and you can still recognize vesicles in this volcanic cluster that of course predate this accumulation of conglomeratic material, because we will learn that conglomerates usually have fairly well-rounded fragments. This is again the same classification we looked earlier, but with another degree of complexity. We look at glass as a key criteria to apply a terminology to the tuffs. So we look at the tuff composition, so glass rock fragments and crystals, and so depending on the abundance you will assign this prefix to the tooth name. And this one is exactly as illustrated earlier. So the classification of pyroclastic rocks can be based on the type of material, so if it's lithic, vitric or crystal rich, or based on the size of the material, which is what we discussed earlier. So I ended up with this summary. I recommend you revise what I've corrected for lecture test 1, and as an assignment I will ask you to discuss the type of volcanic activity found at Mont Sainte-Hélène. In this same lecture there are a number of slides, additional slides about Mont Sainte-Hélène that you can use for your own sake for the research associated with this volcano.